Okay, so computers. Right. I mean, we use them for like everything these days. But how many of us actually know how they, actually work?
Right.
It's kind of like, I don't know, driving a car. You don't need to be a mechanic to get from A to B.
Yeah, yeah.
But like understanding the engine a little bit, it kind of makes the whole ride, I don't know, more interesting.
Absolutely. And it turns out there's a fascinating story behind these machines.
Oh, yeah.
We're going to peel back the layers today. And we're going to start with, get this, the surprisingly ancient roots of computers.
Okay.
All the way to those sleek modern marvels we rely on every single day.
So where are we starting this deep dive? What are we diving into?
So get this, Wikipedia's What is a Computer page.
Okay, cool.
Who knew something so ubiquitous could have such a rich history?
Yeah,
right?
yeah, for sure.
And it all starts with something so basic, but so fundamental to what a computer does.
Okay, what's that?
Counting.
Counting.
Yeah.
Like 1, 2, 3. We're going that far back.
Oh, even further back. Think Babylonia.
Wow.
Thousands of years ago, long before the microchip. Humans were driven by this desire to compute, to make sense of quantities. And you know what they invented along the way?
What's that?
Something you've probably even used yourself.
Okay, now I'm really curious.
The abacus.
Wait, hold on. You're telling me that, colorful counting toy I had as a kid?
Yep.
That's a precursor to, the laptop I'm using right now.
Exactly. The abacus is a testament to how fundamental the need to calculate is and how long humans have been striving to find ways to do it more efficiently. But the abacus wasn't the only ancient marvel.
Oh, there's more.
Oh, yeah. We also have the Antikythera mechanism.
Yeah.
Discovered in a shipwreck.
Antikythera mechanism. Yeah, isn't that like an ancient Greek astronomical clock?
Precisely. Imagine gears and dials, all meticulously crafted, working together to track the movements of the stars and planets.
And how old is this thing?
It dates back to around 100 BCE.
100 BCE. That just blows my mind. The fact that they had that kind of technical know-how back then, it's incredible.
It really is.
But I guess that really underscores your point, this urge to understand, to predict, to compute. It's been with us for a long, long time.
Absolutely. And for a long time, the word computer, it didn't actually refer to a machine at all.
Wait, really? What did it refer to?
A person.
What?
Believe it or not, a computer was a person employed to perform calculations by hand.
Wow. Can you imagine doing that all day, every day?
I know, talk about tedious. And, it's an early example of how gender dynamics played out in this field, even back then.
Yeah.
Because these computers were often women.
Interesting. But I'm guessing things started to change as we moved into the 1800s, right?
They did?
Enter Charles Babbage.
Yes.
And his groundbreaking vision.
Ah, Charles Babbage, a true visionary.
So tell me about him.
He dreamt up this incredible concept, the analytical engine.
Okay.
It was the 1800s, and he's envisioning a mechanical computer powered by steam.
Whoa.
Using punch cards for input.
Hold on. Steam-powered and punch cards. This sounds like something straight out of a steampunk novel.
It really does. But what's even more mind-blowing is that his design, it included concepts that, we consider fundamental to programming today.
Really?
Like conditional branching loops. Babbage was truly a century ahead of his time.
So why wasn't it ever built? What happened?
Well, the complexity of Babbage's vision, that was its biggest hurdle.
Really?
The technology at the time just wasn't there. Building the analytical engine would have required thousands of precisely engineered parts.
Wow.
All made by hand. And the funding just wasn't available to bring such an ambitious project to life.
That's amazing and a little heartbreaking at the same time. So his work, it never saw the light of day.
Not exactly. While Babbage never saw his analytical engine fully realized, his designs, his blueprints of a mechanical computer, they laid the groundwork. They laid the groundwork for the computers we have today. He planted the seeds for a future he wouldn't live to see.
It makes you wonder what Babbage could have accomplished with today's technology.
Right.
But it seems like it took the pressures of the 20th century to really kickstart this computing revolution.
You're absolutely right. The turn of the century brought with it this wave of innovation, fueled in part by, the looming shadow of World War II. This is where things start to get really, really interesting.
Okay.
One of the first major leaps forward came with Konrad Zuse.
Okay.
And his electromechanical computer, the Z3.
The Z3? I've never even heard of that one.
Yeah, it's not as famous as some of the other computers we'll talk about, but it marked an important step.
Okay.
Developed in 1939, right on the brink of the war, the Z3 used relays Think of them like electrical switches
Okay.
to perform calculations.
Mm-hmm.
It was still partly mechanical, but it proved that moving away from purely mechanical computation, that was the way forward.
So it was sort of a stepping stone between those early mechanical calculators and the electronic computers we know today.
Exactly. And speaking of electronic computers, we can't forget about the vacuum tube,
Okay.
the technology that really ushered in the electronic age of computing.
The vacuum tube.
Picture this, right? Glowing glass bulbs, thousands of them, forming the heart of these massive early computers.
Wow.
That's the vacuum tube era in a nutshell.
They sound pretty fragile for being such I don't know, a pivotal part of computing history.
They were. Vacuum tubes, they generated a ton of heat. They were notoriously unreliable, and they were bulky, to say the least.
Yeah.
But compared to earlier technologies, they were a huge step forward.
So they must have been what powered those, like, room-sized computers you see in old photos.
Exactly. The Colossus, built by the British during World War II to crack German codes, that's a prime example of vacuum tube technology in action. It was instrumental in the war effort. It showed the world just how powerful these early electronic computers could be.
Talk about a high-stakes use of computing.
Right.
It's amazing to think that something as complex as code breaking could be done with vacuum tubes.
And then there was ENS, the electronic numerical integrator and computer. It was like the Colossus's bigger, faster, and a way more versatile cousin.
Okay.
We're talking a computer that weighed 30 tons.
Wow.
And took up an entire room.
I've seen pictures, yeah. It was practically a building unto itself.
It was.
I bet it sucked down electricity like nobody's business.
Oh, you're not wrong. ENAC needed enough power to light up a small town. But here's the interesting thing.
What?
It was programmable
Okay.
for a variety of tasks, not just code breaking.
So it was like a real jack of all trades in the computing world. What kind of things was it used for?
Well, initially, it was designed for calculating artillery firing tables for the U.S. Army. But its flexibility allowed it to be used for everything from weather prediction to atomic energy research.
That's incredible.
And here's a fascinating bit of trivia for you. ENIAC was programmed by a team of brilliant women known as the ENIAC Girls.
ENIAC girls. I've never heard of that.
Yeah, they were pioneers in the truest sense of the word. These women were writing programs essentially telling this massive machine what to do at a time when women in STEM fields were incredibly rare. They made significant contributions to ENIAC's success, yet their stories were largely overlooked for decades.
What a powerful reminder that women have always been at the forefront of technological advancement, even when history tries to, I don't know, write them out of the story.
Absolutely.
Yeah.
Their contributions paved the way for future generations of programmers and computer scientists. But let's get back to those vacuum tubes.
Okay.
As groundbreaking as they were, they had some serious limitations.
Yeah, I can't imagine building anything too compact with those things. They just sound bulky.
Yeah, and you're right. Miniaturization was a huge challenge. But even more importantly, those early computers, they lacked a key feature of modern computers.
Okay, what's that?
Stored programs.
Stored programs? What does that even mean?
So before stored programs, if you wanted to change what a computer did, you literally had to rewire the entire machine.
What?
Imagine having to rearrange this giant tangle of wires
Oh my God.
every time you wanted to run a new program. Talk about a nightmare.
That's insane. So stored programs are like having the instructions like saved inside the computer itself.
Precisely.
Oh.
Instead of rewiring for every single task,
Right.
we now have instructions stored in the computer's memory, ready to be accessed and executed at lightning speed.
That's a game changer. It's like the difference between like handwriting a letter every time you want to send the same message versus just hitting like send on an email.
Exactly.
Who do we have to thank for this incredible innovation?
Well, the seed for this revolution was planted back in the 1930s.
Okay.
By none other than Alan Turing,
Okay.
a true genius who also played a pivotal role in breaking the Enigma code during World War II.
Wow.
He envisioned a machine that could store and execute instructions, paving the way for the computers we know and love today.
Wow. Turing's contributions to computing are truly remarkable.
Absolutely. He was a visionary who saw the potential of computers long before most people even understood what a computer was.
Yeah.
And his ideas, they finally became a reality with the Manchester Baby.
The Manchester Baby. What a cute name for a computer.
It is a cute name. But don't let that fool you. It was a technological marvel.
Okay.
Built in England in 1948, the Manchester Baby was the first electronic stored program computer.
So this was it, the dawn of the modern computer age.
Exactly.
Okay.
It might have been small compared to those behemoths like ENIAC.
Right.
But the Manchester Baby, it proved that Turing's concept of a stored program computer, it could actually work.
Wow.
It was a monumental achievement. It changed everything.
It's amazing to think how far we've come from those early room-filling computers to the devices we have today. But I'm guessing the journey to miniaturization, it wasn't easy, right?
You're right, it wasn't. And this is where we need to talk about another groundbreaking invention, the transistor.
Oh, the transistor. Yeah, I remember learning about those in school.
Right?
But I can't say I fully understood, what they did.
Well, imagine you're trying to build a complex machine.
Okay.
But instead of using, I don't know, nuts and bolts, you're stuck using thousands of fragile, glowing light bulbs.
Right.
That was the challenge with vacuum tubes.
Okay, I get it. Not exactly the ideal building blocks for a sophisticated machine.
No.
So where do transistors come in?
So transistors were like tiny solid-state switches that could control the flow of electricity much more efficiently and reliably than vacuum tubes.
Okay.
They were smaller, they generated less heat, and they were way more robust.
So transistors were like the miniaturization revolution in electronics?
Exactly. They paved the way for smaller, faster, and way more affordable computers.
Wow.
And if that wasn't enough, they also led to another game-changing invention, the integrated circuit, or IC.
The integrated circuit, that sounds familiar.
It does, right? Think of it this way.
Hmm.
Imagine shrinking an entire circuit board
Okay.
with all its transistors and components onto a single tiny chip.
Wow.
That's the power of the IC.
Wow. Talk about packing a punch. No wonder our devices are so small and powerful these days.
Exactly. The first working ICs, they were invented in the late 1950s.
Okay.
And from there, the pace of innovation exploded. ICs, they allowed for even more miniaturization
Wow.
and complexity, which ultimately led to the development of the microprocessor.
The microprocessor, the brains of modern computers.
Precisely. The Intel 4004,
Okay.
released in 1971, this was the first single-chip microprocessor. It contained thousands of transistors
Oh.
on a chip the size of your fingernail. Can you believe that?
It's mind-boggling. And today's microprocessors are even more impressive.
Oh,
Wow.
absolutely. Today's microprocessors contain billions of transistors, yet they're still remarkably small.
Wow.
It's a testament to how far we've come since the days of those bulky vacuum tubes.
So we've gone from steam-powered machines and fragile vacuum tubes to microscopic transistors and powerful microprocessors. It's been an incredible journey. But I'm curious, how do all these components actually work together? How is a computer structured?
Most modern computers are based on what's known as the von Neumann architecture.
Okay.
It's like a blueprint. It defines the basic components of a computer
Okay.
and how they interact.
Okay, I'm all ears. Break it down for me. What are the key components of this architecture? All right, so we've got the blueprints, right? The von Neumann architecture.
Yeah.
But what's actually going on inside a computer following those blueprints?
So at the heart of it all is the central processing unit, or CPU.
Okay.
This is where the microprocessor lives.
Right,
It's
right.
basically the brain of the operation.
And what exactly is the CPU doing while I'm, say, writing an email or editing a video?
So the CPU has a few key parts.
Okay.
There's the arithmetic logic unit,
Okay.
or ALU.
ALU.
And as the name suggests, this part handles all the math and logic operations.
So adding numbers, figuring out if one thing is bigger than another, that kind of stuff.
Exactly. And then you have the control unit,
Okay.
which acts like a conductor in an orchestra,
Okay.
making sure all these operations happen in the right sequence.
Right.
It's all about directing traffic inside the CPU to make sure everything runs smoothly.
It's amazing how much is going on behind the scenes that we never even think about.
Right.
So we've got the CPU diligently crunching numbers, keeping things in order. What else is there?
Well, the CPU needs somewhere to store all the data it's working with, right?
Right.
That's where memory comes in.
Okay.
Think of it like the computer's mental workspace.
Okay, and what kind of workspace are we talking about here?
So there are two main types of memory, RAM and ROM.
RAM and ROM.
RAM stands for random access memory.
Okay.
And it's like the computer's short-term memory. It's super fast, which is why the CPU stores the data it's actively working on in RAM.
So if RAM is short-term memory, what about long-term storage? That's where ROM comes in.
You got it. ROM stands for read-only memory. It's more like the computer's long-term memory. It stores the essential instructions the computer needs to like boot up
Okay.
and operate properly, kind of like a brain's hardwired instincts.
So it's like RAM is your desk where you're working on a project, and ROM is like the filing cabinet where you keep important documents that you need to refer to from time to time.
That's a great analogy.
Okay, cool.
And speaking of storage, most of us are familiar with the idea of hard drives and SSDs in our computers.
Right.
Those are examples of even more long-term storage where we keep all our files, our photos, music, everything else.
Right, okay, so that's the CPU memory. What about how we actually interact with this whole system? I mean, I'm typing on a keyboard, looking at a screen. How does a computer know what to do with all that?
So that's where input and output devices come in,
Okay.
or I/O devices.
Oh, okay.
They're like the communication bridge between us and the digital world inside the computer.
So like the keyboard and mouse are inputs, and the screen and speakers are output.
Exactly. Input devices allow us to send information to the computer, while output devices allow the computer to send information back to us.
Okay.
Whether it's text, images, sound, anything. It's how we make sense of what the computer is doing.
So it's like the computer senses and its voice kind of all rolled into one?
Yeah.
Okay, so that's the hardware side of things.
Right.
But what about the software? We've touched on stored programs, but how do we actually like tell the computer what to do with all this hardware?
That's where programming languages come in. They provide a way for humans to write instructions that the computer can understand.
So it's like translating our intentions into a language that the computer can actually speak.
Precisely. And just like there are many different spoken languages,
Right.
there are many different programming languages.
Right.
Each with its own, like, strengths and purposes.
Okay.
But at their core,
Mm.
they all allow us to break down, like, complex tasks
Yeah.
into a series of simple instructions that the computer can follow.
From those basic instructions, we get everything from like simple calculators to complex video games. Right. All thanks to the power of code.
I know.
It's pretty mind-blowing when you think about it.
It really is. And the ending thing is, this is just the tip of the iceberg.
Yeah.
We've come a long way from Babbage's mechanical dreams
Right.
to the devices we have today.
Right.
But the world of computing, it's constantly evolving. There are some, like, truly mind-blowing advancements
Mhm.
on the horizon.
Okay, now you've got me really curious. What kind of future are we talking about here?
Well, one field that has the potential to, like, revolutionize everything, quantum computing.
Quantum computing. That sounds like something straight out of Star Trek.
It's pretty futuristic, yes.
Okay.
So instead of relying on bits, which can be either a 0 or a 1,
Right.
quantum computers, they use qubits.
Yeah.
Which can be both 0 and 1 at the same time.
What?
It's true.
Okay.
This quantum weirdness
Right.
allows them to tackle problems in ways that are just impossible for traditional computers.
So it's like the computers we use now are limited by the laws of physics as we currently understand them.
Right.
But quantum computing is like tapping into a whole new level of reality.
Exactly. It's still early days, but quantum computers, they could one day lead to breakthroughs in everything,
Wow.
from medicine to material science. It's an incredibly exciting field to watch.
So quantum computing is like rewriting the rules of what a computer can do. That's incredible. What else is on the horizon?
Another area that's advancing at an incredible pace, artificial intelligence, or AI.
AI, right.
We're already seeing its impact, like, everywhere, right?
Yeah.
From self-driving cars to medical diagnoses.
Right.
And it's only going to become more prevalent.
Yeah, it seems like every day there's a new headline about AI.
And for good reason. AI has the potential to, like, transform so many aspects of our lives. We're talking about machines that can learn from data, adapt to new situations, even make decisions.
It's both like exciting and a little daunting to think about where AI might lead us.
It definitely raises some big questions.
Yeah.
But one thing is certain. The future of computing is going to be, like, unlike anything we can fully imagine today.
It's amazing to think that something as like seemingly simple as the desire to count has led us to this point. From ancient abacuses to quantum computers, it's been an incredible journey.
It really has. And it's a journey that we're all a part of. Every time you interact with a computer, you're tapping into this rich history of innovation and human ingenuity.
It really makes you appreciate the incredible power and potential of these machines and the brilliant minds who have made it all possible.
It really does. And who knows, maybe one of our listeners will be inspired to join the ranks of those brilliant minds and shape the future of computing themselves.
That's the beauty of a deep dive like this, right? It sparks curiosity.
Yeah.
It opens your mind to new possibilities.
Exactly.
So the next time you open your laptop, you pull out your phone, remember, it's not just a device. It's a testament to human ingenuity, a portal to the future, and maybe even a source of inspiration for your own journey of discovery. Thanks for joining us on this deep dive into the world of computers.